Hello everyone, we present AMT, which is a practical algorithm specifically designed for frame interpolation. AMT stands for all pairs multi-field transforms. It is lightweight, fast, and current. First, let's quickly preview the highlights of the AMT algorithm. AMT is the first raft-style video frame interpolation framework. AMT shows a good trade-off between efficiency and performance. The designs in AMT reduce the difficulties in modeling large motions and handling occluded areas during frame interpolation. It shows the competitive results compared to transformer-based methods. This advantage These advantages can be attributed to the two essential designs. The first is all pairs correlation. The second is multi-field refinement. Combine these two designs enables us to generate promising task-oriented flows. Now we will review that why promising task-oriented flows are important for frame interpolation tasks. Frame interpolation could perform video generation from a few given frames, at least 2 frames. Frame interpolation tasks heavily rely on optical flow estimation to model the motion information of missing frames. For frame interpolation tasks, estimating task-oriented optical flow can effectively improve the quality of the interpolated frames. Thus, the quality of task-oriented optical flow affects the quality of final synthesized frame. As shown in the image, it is challenging to estimate accurate optical flow motion for the person's foot due to the significant motion displacement. If the motion is accurately estimated, the position and contour of the foot can be well synthesized. So what is the promising task-oriented flow? As stated in previous work, task-oriented flow is generally consistent with ground truth optical flow but diverges in local details. Hence, the entire network design follows the characteristics of task-oriented flow. We aim to maintain the consistency of optical flow on coarse scales and improved diversity on the finest scale. We thus involve two essential designs to achieve this goal. The first is all-pair correlation for handling large motions, and the second is multi-field refinement, which is responsible for solving the flow ambiguity in occluded areas. Here is the overview of our framework. We now detail the two designs. For the first design, named all pairs correlation, we first extract initial bilateral flows and the intermediate frames. Then we build bidirectional correlation volumes through transposing the unidirectional correlation volume. After volume construction, we intend to query correlation feature maps using estimated bilateral flows. There exists a mismatch between coordinate system of bidirectional correlation volumes and bilateral flows, which causes unfaithful correlation lookups and further influences the updating of the flows. A straightforward solution to this problem is transferring bilateral flows to bidirectional ones through a simple scaling. Then we update both content feature and bilateral flows with indexed correlations. Note that the lookup operation is conducted across scales. For the multi-field refinement, we first predict multiple groups of bilateral flows and occlusion masks and a content residue using the last decoder. Then we obtain the candidate of each group using traditional backward warping independently. Finally, we merge all candidates using simple convolutions. It is worth noticing that our multi-field refinement can serve as an effective improvement for traditional backward warping. It can serve as a plug-and-play operator for any Wi-Fi framework. Let's first look at some ablation results. We first ablate the all-pairs correlations in our AMT. The network equipped with all-pairs correlation has a stronger ability in large motion modeling. As a result, the performance surges obversely, especially in large motion cases. Then we test the effect of our multi-field refinement compared to the baseline, which has only one pair of flows. The network with multiple flows diminish the ambiguity in occluded regions and achieve a better performance. Note that this operator is very efficient and plug-in, so you can use this operator in any VFF network for a better performance. Now we turn to the quantitative results. This figure shows the comparison among the existing convolution-based methods and ours. We conduct this comparison in 3 dimensions: performance as y-axis, computational cost as x-axis, and the number of parameters as the size of the circle. Our method outperforms the existing convolution-based methods by a large margin with less parameters and flows. We also compare with transformer-based methods. These methods utilize advanced attention blocks. Our method, which uses plain convolutions only, is still highly competitive with the transformer-based ones. Here are the qualitative results in the efficient setting, which presents in the first and second row. None of the previous methods managed to interpret the wind and the occluded background behind the person, while our method is able to provide a current shape and texture. For the large models in the third and fourth row, our method still outperforms the previous. Thanks for watching this video. If you are interested in this paper, and you can scan this QR code and check out our project page, where you can find more video results, ablation studies, interactive demos, and our released code.